Welcome to today's deep dive. We're looking at the latest data and inspection standards from the Dryer Vent Safety Council. Our mission today is to completely dismantle this really common counterintuitive misconception. This idea that pulling a massive clog of gray fuzz out of a shiny metal pipe means your appliance is automatically safe and well-performing.
It's arguably the single biggest mistake property owners and even, some professionals make in this industry, assuming that clean equals safe.
So we're going to look at the actual physics of how your home's exhaust system works, because we have to separate how a vent looks from how it actually performs.
And I think it's a critical distinction. We're exploring this today really just to look objectively at the mechanics of building science. I mean, we're dealing with a system hidden inside your walls that you probably use multiple times a week.
Okay, let's unpack this, though, because I'm stuck on this right from the start. If I pull a giant clog of lint out of my vent, doesn't that inherently fix the airflow?
Well, removing lint is absolutely essential. We definitely can't understate that. When lint is the source of the restriction, getting it out of there will dramatically improve airflow.
Right. Aren't we still fixing part of the problem?
You are. But the issue is that lint is often just the most visible symptom of a much larger aerodynamic problem. We have to think about what the dryer is actually trying to do.
Which is dry, wet clothes.
Right. But physically, how? When you put wet clothes in the drum, the dryer heats the air to absorb that moisture. That hot, heavy, moisture-laden air then has to be evacuated through the ductwork to the outside of your house.
Okay, makes sense.
So the blower motor in your dryer is really only designed to push that heavy air against a certain amount of physical resistance.
And when you say resistance, you mean the air is literally rubbing against the inside of the pipe.
Exactly. In fluid dynamics, they refer to it as static pressure or friction loss. Every foot of pipe adds a little bit of friction.
Oh, wow. Okay.
Yeah, so the longer the duct, the more resistance the air encounters, which slows the velocity of the air down. And if the air slows down too much, it can't carry the heavy moisture.
It just drops it.
Basically, the air cools off inside the pipe, the moisture condenses, and the lint just drops right out of the airstream and sticks to the walls.
So the lint buildup you're seeing isn't always the root cause of the problem.
No, it's often the result of an exhaust system that has too much resistance built into its fundamental design.
So if I clean out the lint, I'm really just treating the symptom. I haven't fixed the reason the air is slowing down in the first place.
Precisely. A clean duct doesn't magically shorten a vent run that was built way too long. It doesn't straighten out a sharp, restrictive elbow joint hidden inside your ceiling.
Wait, elbow joints? Like the turns in the pipe?
Yeah. Every time you force a column of moving air to suddenly change direction, like hitting a 90-degree turn inside a wall, you create massive aerodynamic turbulence. The air just crashes into the wall of the pipe, causing the pressure to spike and the velocity to plummet. You could have a vent that is completely devoid of lint, but if it has 4 90-degree elbows in a tight space, the blower motor in the dryer is just going to choke.
Wow. What other structural roadblocks are we talking about here? Because if we're looking past the lint, what else is physically stopping the air?
The materials themselves play a huge role. I mean, building kinds require smooth, rigid metal ductwork for a reason.
Right.
If a builder or a homeowner uses corrugated flex duct, the stuff that looks like a metallic slinky.
Oh, yeah, I've seen that behind basically every dryer ever.
Exactly. Well, the air has to bounce over every single ridge inside that pipe. That creates immense friction compared to smooth metal. You might also have a section of ductwork inside a wall cavity that was accidentally crushed by a plumber or an electrician during construction.
Just stepped on it or something.
Yeah. Or you might have a hidden booster fan that has failed.
I actually noticed that in the source notes. Why would a dryer vent even have a fan inside of it? Doesn't the dryer push the air?
It does, but in a lot of modern construction, especially condominiums or townhouses, the laundry room is placed right in the center of the house for convenience.
Oh, right, away from the exterior walls.
Exactly. That means the exhaust duct might have to travel 30 or 40 feet just to reach an exterior wall. That distance creates way more static pressure than a standard dryer motor can overcome.
So they add a fan to help it along?
Yep. Builders install secondary mechanical booster fans inside the ductwork, often hidden up in an attic or a crawl space, to help pull the air through that long run.
But mechanical things eventually break.
They always do.
Yeah.
The pressure switch might fail, or the motor might just burn out from age. And here's the really insidious part.
What's that?
A property owner might buy that condo and never even know the hidden booster fan exists.
Oh, no.
Yeah. When that fan stops spinning, the heavy metal blades inside the pipe stop acting like a fan and start acting like a wall.
They just block it.
Right. They become a massive physical blockage right in the middle of your exhaust system. You can brush out the pipe until it shines, but if you have a dead booster fan sitting in the attic, your performance is fundamentally zero.
This highlights a huge limitation with how these systems are typically inspected. I mean, if cleanliness is just a condition, the instinct for most of us, and frankly a lot of technicians, is just to look inside the pipe.
Sure, they use a flashlight, or more likely one of those flexible scoping cameras.
Exactly. But if I'm understanding the physics here, visual data does not equal aerodynamic data.
It doesn't. And we need to be careful here because scoping a line with a camera is an incredibly valuable diagnostic tool.
Oh, for sure.
Sending a camera down a duct reveals conditions we could never see otherwise. It shows you if a joint has pulled apart inside a ceiling and is dumping moisture into your drywall.
Or where the lint actually is.
Right. It identifies damaged materials and obviously shows you exactly where the accumulation is.
Wait, but isn't seeing believing? Like, if I'm standing next to a technician, watching a live camera feed of my vent on a monitor, and the metal walls look perfectly shiny and spotless, shouldn't I feel totally confident?
Well, what's fascinating here is that it's basic human psychology to trust what we see. We suffer from visual confirmation bias.
Okay, explain that.
A technician sees a clean pipe, assumes they've succeeded, and completely ignores the aerodynamic drag of the system as a whole. But think about the physics we just discussed. A camera cannot mathematically calculate the friction coefficient of the materials it's looking at.
Right.
It cannot add up the cumulative pressure drops caused by the length of the run and the multiple elbow joints. It just can't do the math.
It just shows you a picture.
Exactly. A vent that looks completely clean and shiny on a camera monitor can still perform terribly when you actually turn the dryer on because the geometry is fundamentally flawed.
That is wild.
And the reverse of this is also true, which is really interesting. A camera might show a vent that looks visually ugly.
Ugly how?
Maybe the metal has some strange discoloration, or the foil take on the joints looks a little sloppy. Visually, it's imperfect. But functionally, structurally, the airflow might be experiencing very little resistance.
So it's actually fine.
It might be performing within a perfectly acceptable, safe range. Visual information simply answers a completely different question than performance data. Looking at a pipe asks, what is the condition? Measuring asks, what is the performance? Perfectly captures the methodology the Dryer Vent Safety Council emphasizes. Everything has to start line reading before you decide what the system actually needs. You have to establish the vitals.
And in this industry, how does that happen?
That happens through specific performance measurements using specialized instruments.
How do you measure dryer vent performance before and after service?
Right.
If they just hold up a brush and a camera, you know they're only checking the condition. But if they can explain their pressure or velocity testing process, you know you're dealing with someone who understands performance.
I think there's a broader context to leave everyone with today, especially as we think about how homes are evolving. We have completely normalized high-tech, highly calibrated appliances.
But the infrastructure they rely on is stuck in the past.
Exactly. When it comes to the vital exhaust systems that keep those expensive appliances safe, functional, and efficient, we still tend to treat them as dumb, static, invisible tubes.
We just assume that if the tube is empty, everything's perfectly fine.
But as our homes and our appliances continue to get smarter and more precise, shouldn't our expectation for measurable, dynamic performance tracking in our home's hidden infrastructure evolve too?
That is such a good point. It just doesn't make sense to upgrade the machine without verifying the road it travels on. Well, thank you all for joining us on this deep dive into the physics of your home. Keep asking the right questions, demand data over assumptions, and we'll catch you on the next one.